What are ethers? Ethers are compounds with a single bonded oxygen on either side. Okay, compounds with single bonded oxygen. Ethers are compounds with single bonded oxygen. This can be part of the ring. See here, CH3 and CH3. So this is an ether. Or this can be C6H5 or CH3. Okay, so this is an, and it can be a cyclic ether. See, this also is an ether. This is called a tetrahydrofuran. This is dimethyl ether. The most commonly used known ether, which we call as ether in the laboratory, simple ether. It is this compound, diethyl ether. Diethyl ether. Which you call as ether in the laboratory. Just like, when you say alcohol, we mean ether alcohol, right? Very similarly, when you just simply talk ether, it is diethyl ether. This is methyl phenyl ether. It is also called anisole. Anisole. This is tetrahydrofuran or THF, commonly known solvent. THF, tetrahydrofuran. Tetrahydrofuran. Okay, so these are the common ethers which we come across, and you can prepare. Now, cyclic ethers. There is something interesting about the cyclic ether. This is a cyclic ether. It will be having very similar property like this. Even this will be having, of course, this is more unstable. This is more unstable. As it comes here, only 2 carbons. Here you have 3 carbons. Here you have 4 carbons. 1, 2, 3, 4 carbons. Okay, this is also a cyclic ether, but this one, when you have only 2 carbons, this special ether you call as epoxide. When you have only 2 carbons, you call it as epoxide. It is having entirely different properties. It is having entirely different properties that are simple ethers. So we call epoxides are taken care of separately. Epoxides are taken care of separately. Okay. So let us look at the preparation. We have already seen. We have seen the preparation of ethers from alcohols. And also, you can prepare from alkyl halides. In fact, you require both of them. Alkyl halides. So, you combine these two. First, you convert in presence of sodium hydroxide or sodium. You will get ethers. Okay. Now, sodium hydroxide you can use on reactive alcohols. Sodium metal you can use on unreactive alcohol. So there is a general approach. Let us look at, suppose you have C2H5OH. You cannot use sodium hydroxide. You have to use sodium. What will you get? You will get C2H5ONA. ONA. Okay, sodium ethoxide will be obtained. So you have generated a nucleophile, a strong nucleophile. Now you are reacting this with C2H5I, C2CH3, CH2I. See, a primary alkyl halide, a strong nucleophile, primary alkyl halide, attacks on this carbon and forms, this is going out, SN2 mechanism. SN2 mechanism. What will you get? C2H5O, C2H5 plus NaCl. So that is a mechanism of the reaction. Okay, so this is how you form it. Now, if you take only OH, phenol, if you take phenol, and then take, you can simply take sodium hydroxide because this is highly acidic. This is not much acidic, very weakly acidic, very weakly acidic. So, to remove this proton, you require a strong reagent. But this is sufficiently more acidic. I'll use the word more acidic. So you don't require that much a strong reagent. You simply require only sodium hydroxide. The sodium hydroxide will act as a base, will abstract this proton and generate the anion. See here. Generate the anion. Okay. O minus. Now you can Na plus. Na plus. Now that react with CH3I. That will react with CH3I and you will get anisole replacement over here. And this what you call as anisole. Remember, this is a very good perfumery material. this is this is used in perfumery industry. Okay, you can use this. Now, if you take this compound, instead of this, you start with beta-naphthol. Very common reagent. Very common reagent. Do the same reaction. NaOH. You will get the corresponding phenoxide. Okay. And see, this methyl iodide is very costly. Right? Costly. Very costly. And iodine compounds are very costly. So you cannot afford to prepare a cheap reagent for it. So for that, because of that, what people do is they use a cheap raw material, dimethyl sulfate, CH3 twice SO4. This is what is called dimethyl sulfate. This is cheap. You're getting disconnected frequently, right? It's okay, but try it out. So this is dimethyl sulfate, DMS, dimethyl sulfate. And you get another perfumery material. Let me just raise the board. We will get another perfumery material having this structure. This is the structure. Again, an ether. OCH3. This is called a methoxynaphthalene. Methoxynaphthalene. And it's actually beta methoxynaphthalene. Beta. And this is commonly known in chemical as nervogen. And in chemical marketing, okay, what is this? Can you hear me? But I don't think you can see the board, right? Yeah. Yes, okay. I think you can see the board now. Internet connection is very bad. For last 2-3 days, I'm facing this problem. Okay, yeah. So this is commonly known as, and you know, this is used in agarbatis. Agarbatis means chandandiri. Very widely used in agarbatis. Very commonly used in agarbatis. Most of the agarbati which people have the smell, of course, latest one, I'm not very sure. But this is very largely made, and this is manufactured in very large amount. So that is these are the methods of preparation of ethers. Okay. Also, you have to know one more thing. Suppose you want to prepare ether like this. Say you want to prepare OCH3. CH3 on one side, and the other side you want CH3, CH3, CH3. What is the starting material for this? Which starting material will give you this product? Plus, which alcohol on reaction with sodium, and which alkyl halide? How to find the starting material? See this. See. Let us see. We will expand this structure. Expand this structure. CH3. Okay. Now, you can break the bond either here, A, or you can break this bond here, B. So you have a chance of starting with 2 types of alcohol. So this can be obtained from, let me put the halide here first, CH3, Cl plus O minus C. You can do this now, CH3. Or if you break here, you'll get CH3 O minus plus Cl These are the 2 possible starting materials: alkyl halide, tertiary alkyl halide, and methoxide ion, or CH3Cl. CH3Cl and alkoxide. Now, which one will give you the product? which of these two starting material will give you the product. Now here is a strong base and as a strong nucleophile. This can directly attack here and give you the product. But what about here? Here is a strong base. And a strong nucleophile. And a strong nucleophile. Now, here is a tertiary alkyl halide. A tertiary halide. Now, if you want to get this product, this nucleophile has to attack on this carbon. Okay. And not in this direction. It has to, okay, Renisha is there. Renisha coming late. Now, you have to attack this carbon. Attack on the opposite side. And but what happens, we have studied, there is steric hindrance for the approach of this, and therefore elimination will occur, and you will not get the desired product, you will get this product. Elimination product will be. And therefore, this compound will not give you this product. You have to take the starting material. So methyl chloride plus potassium tertiary butoxide or sodium tertiary butoxide will give you this product, not methoxide and alkyl halide. So just keep this in your mind. If you want to prepare, you have to use a small base. You have to use a bulky base and small halide. Here is a bulky base and a small halide. Okay, so this is a preparation. If you use preparation of this. Now, let us look at the reactions of ethers. We will see the reactions of ethers. One second. Let me raise the board. Reactions of ethers. The most ethers are very highly unreactive, in fact. Ethers are highly unreactive. Generally unreactive. And because of that, ethers are used as solvents in many reactions. So used as solvents in many reactions. You know, there is something very interesting about ethers. Like you have THF, diethyl ether and THF. They're used in many reactions like Grignard reaction. Grignard reaction, where you should not have any amount of water. Also, it is used in lithium aluminum hydride reduction reaction. Similarly, many other reactions ethers are used as a solvent because they are inert material. They are chemically unreactive. But you can make them reactive under drastic condition. Like if you take an ether, if you take I should not show this. What is this? If you take an ether and react with an alkyl halide, HX, you will get R4H. Plus RX. And among the HX, HI is the most reactive, then HBr, then HCl. HI is more acidic, we know that. HI is very, very acidic. So this is the order of reactivity. Okay. So for example, if we take this compound, you react in the heat with HI. Heat with hydrogen iodide, you will get C2H5 plus C2H5OH. And one more thing, remember, this will further, if you have excess of HI, this will further react and form I. That also will happen. Okay. So these are ethers. And then we have another class of compounds which are called crown ethers. Compounds known as crown ethers. Certain important compounds known as crown ethers. Now, what are crown ethers? Let us see. Ethers with a cyclic rings containing more number of oxygen atoms. See, for example, look here. Structures are interesting structures. See here. This is a crown ether. Interesting naming they have. They got interesting naming. Now look at the total number of atoms inside. Okay. So you have now got the total number of atoms here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you have 12 atoms. This is the naming of the compound. Right? Now you have 12 here. You write 12 there. Now you write the word crown. And now you count the number of oxygen atoms. Okay. So this is one crown. You can have still more crown ethers you can have. You can increase this number of ether rings. Now this one. Look at this. How will you name them? Instead of 12, you have how many atoms? 4 here, 4, 4. Then here you have 5, so 13, and 2, 15. 15 crown, 5. So this is okay. So these are the names of crown leaders. And synthesis of crown eaters. Different methods you have. This one method I'll show you. You take category. You take category and react with a dihalo compound in presence of sodium hydroxide. So if you react with sodium hydroxide, this compound, NaOH, it will give you O minus, O minus, O minus. Now you react this with an alkyl halide, a long chain alkyl halide like Cl, CH2, CH2O, CH2. Okay, now this will attack here, and this will chlorino, and similarly this will attack here. Oh, okay. Now, not that way. And now you suppose you have two molecules of this. If you have two molecules of this, then you will have this one. Yeah. Now this is going off like. Then just 1 second. Now, so what will you get here? You will get it reacts only once. Remember, reaction conditions are very important here. Now, O once. CS2 and CS2 Cl. Okay. Now you have two molecules of this. O minus, again O minus, and a second molecule here. There is a second group, and here also there is a second molecule, which will generate this compound. So your crown either is going to be having this structure, so you are going to bind it here. Okay, see here. Now, how will you name this compound? So count the number of atoms in the ring. How many 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you have 18 crown. 1, 2, 3, 4, 5, 6, and dibenzo. Dibenzo 18 crown 6. Dibenzo 18 crown 6. Now, so these are the compounds. Now, what is the importance of this? These are having a very important ability to form complexes. They have good ability to form complexes. To form complexes. To form complexes. Okay. Now, how do they say? For example, it looks like, see here, a closed cage, and metal ions can complex here. See, positive metal ion, they can form complexes here. Oxygen will act as ligand. See here. Similarly here, and see, depending on the size of this ring, different metals can selectively complex. Okay, form complexes with different metals. Selectively, depending on the size of the metal, depending on size of metal and ring. Metal and ring. Okay. And therefore, you can use this for purification of wastewater, like removal of metal ions from water. Okay. And also you can use them as selective binding. Separate one ion from a solution, but retain the other one. So you can use, see, the sodium is a larger, sodium is smaller than potassium. So you may require a bigger ether to trap potassium. Okay, so you can selectively use it. Second application is they are used as a catalyst in many reactions. Catalysis in many reactions, which are known as phase transfer catalyst. Phase transfer catalyst. And they are also used in resolution of racemic mixtures. Used in resolution